Welcome to The Explainer. Today, we're going to peel back the layers and take an inside-out journey to really understand how a computer works, from its silicon heart all the way to the global cloud. You know, it really feels like magic, right? But it's not. It's actually this fascinating chain of events, a journey that kicks off with a tiny electrical pulse and ends with you being connected to pretty much the entire world. So let's start at the very beginning.
All right, so let's start at the very heart of the machine. We're talking about the physical parts, the hardware that give the computer its structure and all the raw power it needs to do anything. The best way to think of the motherboard is as the computer's central nervous system. It's this big circuit board that physically connects everything, letting the brain, the memory, and all the other parts talk to each other. Without it, you've just got a bunch of expensive parts that can't communicate.
So you might be asking, why silicon of all things? Well, it has this incredible property. It's a semiconductor. That just means we can control whether it conducts electricity or not. And that simple on or off state is the physical foundation for all binary code, the zeros and ones that are the basic language of every computer. It's what lets us pack billions of tiny switches onto a single chip.
Okay, so if the motherboard is the nervous system, then the CPU is without a doubt the brain. And deep inside that brain is the ALU. This is where the real thinking gets done. All the math, all the logic, like, is this number bigger than that one? Every single thing you do gets broken down into millions or even billions of these super simple operations that the ALU just blitzes through at mind-boggling speeds.
Okay, so we've got the brain. But what good is a brain if it can't remember anything? So now, let's explore how a computer holds on to information, both for what it's doing right now and for the long haul.
The key distinction here is between volatile and non-volatile. Here's an easy way to think about it. RAM is your desk space. It holds everything you're currently working on. But when you shut down for the day, turn off the power, that desk gets totally cleared off. ROM, on the other hand, that's your bookshelf. The info is permanent, ready and waiting, even with no power.
And, you know, not all permanent memory is the same. It really evolved over time. The original ROM was literally read-only. You couldn't change it. Then we got EEPROM, which you could erase with UV light. A bit clunky. And then came EEPROM, which could be rewritten with a simple electrical charge. And that right there is the game changer that lets us do things like update the software on our phones today.
And this table perfectly shows why not all memory is equally fast. It's all about speed and location. Registers are the absolute fastest because they're literally built right into the CPU. Cache is a smaller, super fast chunk of memory that acts as a buffer. The computer is smart enough to keep the stuff you use most often in the cache, so the CPU doesn't have to make that long, slow trip, and we're talking nanoseconds, but in computer time that's an eternity, all the way out to the main RAM.
You know, all this hardware we've been talking about? It's really just a very expensive paperweight until software comes along to tell it what to do. This is the ghost in the machine, the set of instructions that actually brings all the physical parts to life.
So the second you hit that power button, the very first piece of software that wakes up is the BIOS. It lives on a little ROM chip, and its one job is to do a quick health check on all your hardware, and then it's like a drill sergeant shouting, "Wake up!" to the main operating system. It's that critical first handshake between hardware and software.
So when we talk about software, it really breaks down into two main teams. You've got your system software, like Windows or Linux, which is the foundation that manages all the hardware. And then, sitting right on top of that, are all the apps you actually use every day. Your web browser, your word processor, all that stuff.
I mean, it's hard to imagine now, but for a long time, using a computer meant staring at a black screen and typing in these really cryptic commands. The invention of the GUI, well, it changed everything. Suddenly, by using icons and a mouse, anyone could use a computer, not just the experts. It made computing accessible to all of us.
All right, our computer is up and running. It's got a brain, memory, software, but it's kind of lonely, right? Not very useful if it's just sitting there by itself. So let's talk about how it connects with you and, well, the entire world.
So how do we talk to the computer, and how does it talk back to us? Well, it's a two-way street. We give it info with input devices, like a keyboard. The computer gives us info back with output devices, like a monitor. And then you have these brilliant things, like a touchscreen, which do both jobs at once.
When we talk about connecting, the ultimate connection is the web, right? And what's just wild is how fast it all happened. In 1989, it was just an idea on paper. By 91, it was out in the open. And by 1993, with the first really popular browser, Mosaic, the clickable, visual web we all know and love started to take over the world.
You know, the whole magic of the web really boils down to these three core technologies working together. HTML is the language to build the pages. The URL is the unique address to find them. And HTTP is the set of rules for how to send those pages back and forth across the network. That's it. That's the foundation of everything.
Okay, let's clear something up that trips a lot of people up. The difference between a browser and a search engine. The analogy is perfect. Your browser, like Chrome, is the car. It's what you use to drive around the web. The search engine, like Google, is the map you use inside the car to find where you're going. Two different things, but they work together perfectly.
Every single thing connected to the internet needs a unique address. That's its IP address. It's just like a mailing address for your computer. And why the switch from the old IPv4 to the new IPv6? Simple. With IPv4, we were literally running out of addresses. Think about it. Phones, watches, smart fridges, everything needed its own unique address. And we just needed a much, much bigger system.
So all this connectivity is amazing, it's powerful, but it also opens up a few doors we'd rather keep shut. So to wrap things up, let's talk about some basic but crucial ways to stay safe out there. You see that little S at the end of HTTP? That S is your best friend online. It stands for secure, and it means your conversation with that website is scrambled and encrypted. So, my advice? Always look for that S and a little padlock icon in your address bar, especially if you're typing in a password or a credit card number. It's a simple check that makes a huge difference.
So, what about the bad guys? Well, malware, malicious software, comes in a few different nasty flavors. You've got the worm, which is basically obsessed with copying itself and spreading to as many computers as possible. Then there's the Trojan horse, which tricks you by pretending to be a useful program. And finally, spyware, which is exactly as creepy as it sounds. It just hides in the background, watching what you do and stealing your info.
Look, your number one defense, the front door lock to your entire digital life, is your password. And making a strong one is actually pretty simple. Don't just use a word or a name. Mix it all up. Use uppercase letters, lowercase letters, numbers, and symbols. The more you mix, the exponentially harder you make it for anyone to break in. You know, when you step back and think about it, we've gone from computers that filled entire rooms with vacuum tubes to a global network that fits in our pocket. The journey has been absolutely incredible. And now that you know the fundamental building blocks, it really makes you wonder, what's the next great leap going to be?